field theory in flat and curved spacetimes. This is work with Rainer Ferch, and also a very recent paper with Henning Bostelmann, my colleague, and a student, Maximilian Rupp in York. So, if I now move on. So these three subjects, measurement, relativity, and quantum theory, are what I'm going to talk about. And these are quite funny in that if you put any two of them together, there's not too much trouble. Measurement and relativity go together very well. Relativity and quantum theory go very well together. We have quantum field theory. And although measurement and quantum theory are quite controversial sometimes, at least there are clear rules that we can explain to undergraduates, and nobody seems to be in too much of a difficulty in knowing what to calculate whenever they need to. But if you put the three together, there are some curious constraints that come in. So let's go through some of those. It's a complicated business. And the first constraint comes from the fact that the speed of light is finite. And that already means that we know that measurements have to occupy bounded regions of space-time. So if you get your funding and you can then start your experiment, there's only a finite space-time volume available to you before you're going to have to bring the whole thing to an end and do the reporting. So measurements occupy finite volumes of space-time. But on the other hand, because Planck's constant is non-zero, we know that the measurements can't be performed at points because of uncertainty type constraints. We know that that would require arbitrarily large amounts of energy to get point-like measurements. Third observation is that because we've got Lorentz invariance, we know there are no preferred frames. So we can't do what we would normally do in quantum mechanics and invoke an instantaneous collapse of the wave function at some constant time. Instead, you have to do something Lorentz invariant. Well, one way of doing that is perhaps what Helvig and Krauss suggested back in the late 60s, which is to say that the state gets reduced not at a surface of constant time, but rather along the backward light cone of the observation region. That would be at least a Lorentz invariant way of doing things. Fourth observation is we have got relativity of simultaneity, which means that if we have two space-like separated observation regions, we can't possibly decide which of them is first and which is second. So any rules we have for measurement, successive measurement, had better not put a particular order on the two measurements in this situation. And finally, of course, when we go to curved space-time, we get lots more complications. We can have, in general, no symmetries at all to help us out, and we might have non-trivial topology and goodness knows what to deal with. So there's a whole bunch of complications, and the general moral of the story is that if you try to make up what the rules are for quantum measurement theory in quantum field theory, you'll find yourself dancing around all of these various constraints. It's a non-trivial business, and it risks running into pathologies against these sorts of constraints or some others that we might not have thought of yet. And here is an example. Yeah, sure.
Sorry, the previous slide that you had.
Yeah.
Can I ask about just, the first 2 points that you raised? Why do you say, so are you saying the uncertainty principle doesn't tell me that I can't make a measurement at a point, does it? I mean, I would usually interpret it as, for example, I could make a measurement. You've got the energy, frequency,
sure.
frequency. So the usual interpretation of that is that I can still make a measurement at an arbitrary short time, just like the position momentum uncertainty relation doesn't tell me that I can't measure the field at a particular point in space.
Well,
so
I think, no, I would argue that it does tell you that you can't measure at a point. You need, another way of saying it is that to resolve very small distances, you need very high frequencies. Very high frequencies give you very high energies. So if you actually want to measure at a specific point, you are going to need a very large amount of energy at your disposal just to get the right resolving power. That's the what I'm getting at here.
Okay, I'm worried this might take us into a long discussion, which may or may not be relevant to your talk.
Yes.
But I guess that, and so maybe, so okay, I'll leave it as maybe something I don't agree with, but I won't.
Okay.
I'll leave it at that.
Something else.
And if it comes up, maybe I can ask you more about it.
Yeah, certainly.
And the first point.
Certainly.
The first point as well, what stops me from having many observers at different points in space who
of course you can, but suppose you've got a 3-year research project and you get the funding.
Okay.
You can hardly tell your collaborator on Alpha Centauri to get going if you want to get your results back within the time of the grant. Okay, good. That's the idea. Okay. So we've got these 2 constraints. One is you've got to work in finite volumes. You can't possibly measure anything global. And secondly, I also say that you can't measure its individual space-time points.
Okay, maybe I'll clarify this second point with a question, which is the position of the detector is x, and the momentum is the momentum of the particle, say, and those 2 things commute because they're 2, one is the place that I'm performing the measurement and one is the position and momentum of the particle. Those are 2 separate things. So I guess what you're saying is somehow consistent with that. You wouldn't disagree with that, I take it. So
no,
I could know the position of my detector, and that commutes perfectly with the momentum of the particle I'm trying to measure.
I think maybe by writing it down as an uncertainty relation, I've muddied the waters. This is a suggestive picture to go along with the idea that you can't hope to resolve down to individual infinitesimal points. Basically, that's the claim. That's purely and simply what I'm saying. There are theorems, by the way, which back that up in rigorous quantum field theory that say there are simply no observables that are localized at points, at individual points. You can try to say, right, what are the observables in this region, and then narrow it down and down and down and down and down, and the intersection of those algebras is just multiples of the unit. So there are no non-trivial observables you can see. So that's another way of getting at this prohibition on points. Okay. So right. So just now going to the Sorkin example again. So Sorkin in 1993 wrote a paper called Impossible Measurements in Quantum Field Theory. And what he did was to say, well, it doesn't seem that anybody has clearly written down the rules for quantum measurement in quantum field theory. You can write some down. So he more or less by hand extends the rules to quantum field theory. And then he realized that he had run into a pathology, a very interesting one. He said, well, consider 3 experimental regions, A, B, and C. And because they're not points, we can set them up so that A, or the B is partly in the future of A and partly in the past of C, but that A and C are space-like separated. So A and C ought to be able to get on with their business without knowing about each other. But the fact that we have this intervening region B allowed him to make some claim that in fact, sorry if I lost there it is, that if you make a non-selective measurement of a typical observable in region B, then C would be able to determine whether or not A had conducted a measurement. And that would be like a form of superluminal communication between the A and C, which he deemed impossible. I think we'd agree, and said, hello?
Chris, do you mind clarifying exactly what you mean by non-selective?
Okay. So the measurement, B makes a measurement, but the result is not revealed to anybody. Indeed, it may as well be destroyed.
Okay, thank you.
Yeah. So this measurement apparently allows A to communicate to C and therefore should be deemed impossible. But on the other hand, Sorkin had argued that this would apply for a fairly large class of observables you might want to discuss in region B. So he made some strong claims from that. I just want to emphasize that the space-time extension of B is critical, otherwise we wouldn't be able to have this partial overlap phenomenon. But Sorkin wrote that it becomes unclear for quantum field theory which observables can be measured consistently with causality and which can't, and that therefore quantum field theory is deprived of any definite measurement theory. So the idea of what can actually be measured is at best a case-by-case analysis. So that was Sorkin in 1993, and I think it illustrates the pitfalls of trying to extend by hand the rules of quantum mechanics to quantum field theory, because there are very many situations like this, and maybe others you could imagine, where you would run into problems. So instead of doing this, what Rainer Fersch and I did was to take an operational approach. We don't want to just guess or make up the rules for quantum measurement, but we're going to model the measurement process. And in so doing, that brings together two subjects. So in quantum mechanics, there is a well-developed theory called quantum measurement theory. It describes how observables are measured using probes. So this exists, it's well developed, quite successful, but it is very rarely discussed in quantum field theory at all, and still less in curved spacetimes. So there's one gap. On the other hand, there's another subject, algebraic quantum field theory, which is also very successful and founded on the idea of local observables. But on the other hand, if you look in the literature, you find that very little is ever said about how you would actually measure these local observables. So these two theories, which were developed actually by people who were in relatively close contact with each other, seem to have just failed to connect over the past decades even. And that's what we're intending to do in this talk. Basically, we're going to develop quantum measurement theory for algebraic quantum field theory. That should provide better operational foundations for both of those subjects, and it's aimed to give concrete results in models that you could actually calculate. And the slogan is that we're going to take measurement theory out of Hilbert space and put it back in space-time where it belongs. I think somebody once made a joke about taking crime out of the White House and putting it back on the streets where it belongs. Well, we're doing the same for measurement theory. So let's start with some general ideas. What are we doing in measurement? We're taking one part of the world and we're using it to learn about another. And we'll call the first part the probe and the second the system. So there has to be some sort of coupling between the probe and the system, and we have to be able to control it in order to decide whether or not to do the experiment in the first place, among other things. So we have to have some idea of being able to prepare the probe and the system independently, and we need to have some way of measuring the probe in isolation from the system. And then there's a funny linguistic point here, because what we actually have in the laboratory is the system where the system and the probe are coupled together. But we always describe what we're doing in terms of an uncoupled fictitious system. We talk about preparing the probe, preparing the system, measuring the probe, whereas actually all the time we're working on this coupled setup. So there's this shift of language that we have to be aware of when we're discussing these things. So here's the scenario. We're going to take a quantum field theory, which is going to be our system, and we're going to couple it to another one, which is going to be called the probe. We're going to make the coupling operative only in a finite region of space-time, a compact space-time region. And then we're going to measure the probe somewhere else. And we want to interpret all of this in terms of the system by itself. We want to talk about preparing a system, making a measurement on the system, and then afterwards there should be some new state. So these are the sorts of things that we would like to get at, but we're going to access it by talking about this coupled system. So becoming a little bit more systematic about what we're doing. These quantum field theories will be called A and B. We put them on a space-time that I'll denote M. For those who know, it's going to be a globally hyperbolic spacetime, which really means that there are Cauchy surfaces from which ought to determine everything about the dynamics. And I'm going to use a notation that A of M is the algebra of the observables. And if it's an A of M, then it would be the system observables on M. If it was a B of M, it would be the algebra of probe observables on M. So that's with those theories by themselves. Now we can try to put them together in such a way that there is no actual coupling between them, a sort of trivial way of coupling them together. And we can also consider some way of coupling them inside our coupling region K. So here is K. To define an in region and an out region, because we want everything to be covariant, we don't want to invoke any time coordinates or anything like that. So we have geometrical ideas of what the in and out region should be. And we do this basically by obtaining the in region by excising the future of our coupling region. So the future of the coupling region would be J plus of K, as usual notation. And so we excise that to get at the M minus, the in region. And likewise, to get at the out region, what we do is excise the past of the coupling region. This is the causal past, basically cut out its past light cone. So in these in and out regions, the coupling is switched off, so the uncoupled combination and the coupled combination ought to agree. That is going to give us some identifications between these theories, because the in and out regions are going to be big enough to contain Cauchy surfaces, and in fact in this globally hyperbolic setting with K compact, then M plus and M minus always do contain Cauchy surfaces. That should be enough to fix everything, and that means that we can assume that there were identities in the uncoupled combination and the coupled combination. One for early times coming from the M minus, and another one for late times coming from M plus. Using the uncoupled language, what we're going to do is prepare the system and probe separately at early times, and then we're going to measure a probe observable at late times. Now, those are statements about the uncoupled system. Of course, the measurement is made on the coupled system, and what we do is use these identifications, Tor plus and minus, to translate the uncoupled ideas into the actual coupled system. And then, after all of that, we're going to interpret the measurement that's made of the coupled system in terms of the system by itself. We're going to look for a system observable that describes everything that happened. In case you're wondering how can you change the couplings in quantum field theory, well, this is a cartoon that shows you a way of doing it. You imagine fields phi1, phi2, psi1, and psi2, and imagine that there is an interaction term between these various fields that's actually switched on everywhere in space-time. But then we prepare psi1 and psi2 to be switched on only in sort of beams which intersect in some compact region of space-time. And the effect of that is that this interaction term, which has the product of psi1 and psi2 sitting in there, is only really going to be switched on in this compact region of space-time.
I'm going to be making banana cakes.
Hello? I got some, I got an interjection there. Is that a question?
No, it was not a question. I think it was just someone's mic.
Okay. So using an interaction term like that, we managed to get a tunable coupling between the fields that we're interested in, phi1 and phi2. So that gives you an idea of how we might go around changing the couplings between quantum fields. Really, this idea of a compact region is a sort of proxy for the experimental design. So now I want to tell you briefly about algebraic quantum field theory. It's a very general way of describing quantum fields. We use the idea that all of the local observables of the theory can be collected together in a star algebra. So that means that we can form linear combinations, products, we can apply a star operation like the Hermitian conjugation to those elements as well. It's going to have a unit operator, and for every open region, suitable open region anyway, there should be a subalgebra of AM, which corresponds to the observables localizable in that region. Now, there are axioms that come along with this setup, one of which is isotony, which is if we have two regions, one nested inside the other, then the corresponding subalgebras should be nested in the same way. Okay, so the bigger the region N is, the bigger the subalgebra AMN is. Another important assumption is the time slice axiom. And this says that if our little region N is big enough that it contains a Cauchy surface for the full space-time, then the algebra for that region is the same as the algebra of all observables. And that's a way of saying that knowing about a neighborhood of a Cauchy surface is enough to fix everything about the theory. And then the last of the general assumptions we'll use, well, there's one more I'll tell you about later, is the Einstein Causality, which says that if you have algebras for regions N1 and N2 that are causally disjoint, so space-like separated, then their algebras commute. Okay, so that's commutation at space-like separation. And something to bear in mind in all of this is that if you have a given observable, then it can sit in many of these local algebras. Of course, if it sits in this one, for example, then obviously it sits in that one. If it sits in, well, any observable at all sits in AM, and therefore it sits in this region. It's localizable in region N as well, near the Cauchy surface.
Chris, maybe you said it already, but are these observables ought to be local?
Yes, so AM should be the collection of all local observables in the of the theory. Yes.
Okay.
And so the interpretation, as I say, is that AMN should be this algebra here. This should be interpreted as the observables localizable in region N. That's our basic picture here. This looks different from Hilbert space quantum mechanics or quantum field theory, because there is indeed no Hilbert space yet. Instead, there's an abstract idea of what a state is, and that is simply it's a linear functional on the space of all observables, which maps each observable to the corresponding expectation value. So it's an expectation value map, if you like. And as I said just now, the interpretation of an element of this algebra AMN is that it's an observable, localizable in this region N, if it's self-adjoint, or otherwise you might think of it as some sort of operation that you can perform in that region in general. But this is the general structure, and this is really an interpretation. There's very little else to back that up. And in the most of the literature on algebraic quantum field theory, you don't find any discussion of how you actually go about measuring any of these observables or performing any of those operations. So that's the framework we're going to use, and by putting it together with quantum measurement theory, we're going to try to make this interpretation somewhat tighter. And now I can give you a little more detail on how we model the coupled theories. So we're going to have a system and a probe. Those are going to be quantum field theories A and B. If we want to have the uncoupled combination, we simply take a tensor product. So that's a very simple thing to do. For the coupled theory, I don't want to specify Lagrangians or anything like that. I just want to have a very general axiomatic idea of what it would be to, for a theory C to be a coupled combination of these two theories with a coupling region K. And a sort of minimal definition is that whenever you're outside the causal hull of this region K, and the causal hull is the, by the way, is the intersection of the causal future and the causal past of K. If you're outside that causal hull, then there ought to be an isomorphism from the uncoupled combination to the coupled combination corresponding to that region, and also importantly compatible with the isotony relations that I said just above, that if one region is contained in another one, then the algebras have to nest in the right way. Okay, so that's an abstract idea of what it means for the theory C to be a coupled combination of A and B in this with a coupling region that's compact and called K. We can immediately get something out of this in the following way. Let's think about our out region M+. Because M+ contains a Cauchy surface, then the time slice property allows us to build isomorphisms between the uncoupled and the coupled combinations. And it goes like this. Because of time slice, the full algebra is equal to the algebra just for the out region, say the M+. But M+ is, of course, outside the causal hull of K. And therefore, there is supposed to be an identification, an isomorphism between the algebra of the uncoupled combination for M+, and the algebra of the coupled combination for M+. And then we can again use the time slice axiom, but this time for theory C, and deduce that this algebra is nothing but the full algebra for theory C. So in this way, we manage to get an isomorphism that runs from the uncoupled theory on the whole of space-time to the coupled one. And it somehow knows about M+. And we can do the same if we look at the M- region, the in region. So we get these two isomorphisms, and those are going to be the identifications I was talking about before. So the upshot of our abstract definition of coupled combination is that we have these covariantly described advanced and retarded response maps, I'll call them, Tor- and Tor+. So these identify our uncoupled and coupled combinations at early or late times. And if we put them together, of course, so if we first identify at late times and then invert the identification at early times, we get a map from the uncoupled theory to itself, which is an isomorphism. So it's an automorphism of this algebra. So this is going to be called the scattering map, and it plays an important role in what follows. And you can derive a number of locality properties of this map. And the most important is that if you restrict it, if you restrict that scattering map to elements of the uncoupled combination that are localizable in the causal complement of the coupling region, then the scattering map is actually trivial on such elements. So it just doesn't change anything in the causal complement of the coupling region, which is a way of expressing the locality of the interactions that you're using. Okay, are there any questions to this point?
Can I ask
No?
a quick question?
Yeah.
So it's quite abstract. Is the time slice axiom base? Is that like saying the dynamics is somewhat unitary, and this map seems similar to the interaction picture, at least outside?
Yeah, it is very similar to an interaction picture type setup. We can say, so going back to time slice, yes, it's a very abstract form of dynamics, okay? It just says, if you know about a Cauchy surface or a neighborhood of a Cauchy surface, then you know the whole theory, okay? So as you'll see, I've not specified any Lagrangians or anything like that. And this is, so I can't say anything about the field equations as such, but this is a sort of abstract way of saying that there is some sort of underlying dynamics which is rather like the way that hyperbolic equations behave on space-times. Okay, and then here, indeed, our maps, Tor+ and Tor- are rather like taking us to some sort of interaction picture.
Okay, thank you.
Good. Okay, so that's the setup, and we can now describe the measurement scheme, and it comes with a slogan, which is you prepare early and you measure late. You're welcome to do it the other way around, but it's usually less successful. So what we do is we are going to describe a measurement that takes place in the coupled system, but we're going to do it using uncoupled language, if you like. So we fix the system state, omega, and a probe preparation state, sigma. So omega tensor sigma is a state of the uncoupled combination corresponding to these two states. It's clearly got no correlations between them. To map that across to the coupled theory, we want to make an identification at early times, and we use the inverse, the adjoint to the inverse of this identification map Tor minus. And so there's the dual map, I should say. And here it is in formula. If you want to evaluate this state on some observable of the coupled system, X, then firstly what you do is map back using Tor minus inverse to the uncoupled system, keep doing that. And then you can take the expectation of the resulting observable in this uncorrelated state, omega tensor sigma. So this state, the under tilde omega sigma, is going to be regarded as an uncorrelated state at early times, but it's of the coupled system. So it isn't just this simple tensor product form. It's been manipulated by Tor minus, and is now a state of a different theory. So that's a state. Also, we want to be able to talk about measuring degrees of freedom of the probe at late times. And again, if we were looking at the uncoupled combination, we would maybe say, well, take an observable that's identity tensor B, where B is a typical probe observable, couple that together with the unit, and then that should be an observable of this uncoupled combination that is, strictly speaking, only testing probe degrees of freedom. But we want to describe this in terms of the coupled system, so we apply this identification map Tor plus, so that we can identify this as an observable that tests probe degrees of freedom at late times. That's the picture we've got. So what we're actually going to do is measure this observable, B tilde, in this state. Okay, that's what we will do. But we want to interpret the result as a result of measuring a system observable, A, we don't know what it is yet, in our state omega. And the way we decide what A should be is that we want the right expectation value. So there is the expectation value we actually obtain in the measurement. Okay, we use omega tilde sigma to compute the expectation value of B tilde. And we want to find an observable A so that when we take the expectation value in our system state, we get the right answer. Okay. Now we can compute what this is because we use the identification map Tor plus to go across, and then we also had Tor minus inverse in the background. And so one-line calculation shows you that the result is actually equal to evaluating the identity tensor B, applying the scattering map, and then evaluating that in state omega tensor sigma. Okay, so we can convert all of what we're doing back into the uncoupled system in this way. So our problem now is a mathematical one of finding A so that this relation is satisfied here. And that's easily done. Let's consider it in general terms. So imagine we actually had P tensor Q, and we take the expectation value in omega tensor sigma. Well, of course, we just get the product of the two expectation values, but the expectation value is linear. So I can take this factor here inside and say, well, it's just evaluating the system state on this observable here. Okay, so what we can then do is extend the map that sends P tensor Q to sigma of Q times P. We can extend that to a linear map of A tensor B mapping to A. Okay, and then that map, E to sigma, is the right thing to put here so that our expectation value in the tensor product can be written as an expectation value in the system by itself. For those who know about these things, this is essentially a conditional expectation map. So what we actually had to do, if you recall, was to find an operator A whose expectation value in state omega is the same as this expression here. And what we just said shows that the right value for A is going to be to take identity tensor B, apply theta, the scattering map, and then apply this conditional expectation. And all of that I'm going to package together as a single map, epsilon sub sigma. Of course, it depends on the preparation state, which is why probe preparation state, which is why I keep that in place there. Okay, so what we've done now is find a observable in the system that behaves in a similar way to this actual observation on the coupled system. And I'm going to call that then the induced system observable that corresponds to the probe observable we actually, or the probe degrees of freedom, the observation of the probe that we wanted to make in the first place. And in the language of quantum measurement theory, what you would do is package together the coupled theory, these response maps, the probe preparation state, and the probe observable, and say that all of that constitutes a measurement scheme for this system observable epsilon sigma B. Okay, so what we've done now is describe how a measurement scheme can be implemented in quantum field theory. But of course, what we want to do is discover that this also has some nice properties, and we can now go to that. So the first set of properties concern localization, and we use the fact that the scattering map acts rather trivially, well, it acts entirely trivially on regions in the causal complement of the coupling region. So if here is K and there is a little region in its causal complement, then the scattering map should act trivially on observables localizable in L. And that has the following consequence. If we take an observable of the probe that is actually localizable in the causal complement, so if a probe observable lives here, then the observable it induces in the system is just a scalar multiple of the unit. Okay, so there the scalar multiple is the expectation value in the probe preparation state. So this is a completely useless observable to have. It tells us nothing about the system whatsoever, and that's good, because you would rather hope that you can't actually learn anything about the system by coupling in, by measuring a probe outside the causal, causal future or past of the coupling region, because this really shouldn't know about anything that goes on there. So that's the first result, which is a sanity check. The second is that if we now take a system observable A that is localizable in the causal complement of the coupling region, so now we're looking at a system observable in here, then this actually turns out to commute with all of the induced system observables we'll get using this method. Okay, so they just always commute. And that allows us to specify some localization a bit more precisely. In algebraic quantum field theory, there is something called Hague duality, which basically says that if you commute with all of the observables localizable in the causal complement of some region, then your observable must live in that region, more or less. And so if we make the assumption that we have something like that Hague duality going on, then we can say that our induced system observables actually can be localized in any open, connected, causally convex set that contains our region, our coupling region K. So the sort of minimal region for that is the causal hull itself. It just has to be, we want these sets to be open, so it just has to be some small neighborhood of that causal hull. And a very intriguing point about this is that the localization of B was irrelevant in this. All observables of the probe that you could measure will give us induced system observables living in the coupling region. Okay, so whenever we measure a probe whenever we make an observation of a probe, we are actually measuring a system observable localized in this region here. And this you could regard as supporting the idea that this algebra AMN indeed consists of observables that are measurable in that region. Okay. Any questions at this point? No? Okay.
Yeah,
Yeah. Sure.
I feel like could you maybe restate this theorem from a physical point of view? So it sounds like you're saying, I guess I'm trying to relate it to some results I know from quantum information theory in terms of, I guess there's a different language in terms of measurements which are localizable and measurements which are causal. So it sounds like, what's the physical statement that you would make here in terms of
okay,
perform a measurement in any region which is which the probe can causally access, or just which is localizable? I guess I would have imagined that you could make a measurement in any region.
Yeah. So remember that the probe is a quantum field theory. Yeah. So you can make measurements on that quantum field theory wherever you want. Okay. I'm going to assume that we know how to measure the probe somehow. Okay. I'm really describing a step in the measurement chain rather than the whole measurement process. But if we can make a measurement of the probe anywhere we want, that can be interpreted as measuring an observable of the system field, and that observation of the system field is localized around this coupling region K.
Okay, so this is a statement in some sense, a chain statement, meaning,
yes,
am I right, that I can have a probe field and a field that I'm trying to measure, and
yes,
there's this interaction that you set up at the beginning with which turns on and off, and this is a statement saying that this is possible. I can always use a probe to perform a measurement in any region under which I have this interaction that turns on and off.
Yes.
Is that okay?
Yes, exactly. And the thing is that you might worry, and in fact, to start with, we didn't quite know what we would find, that maybe when you make your probe measurement, then this is to be regarded as somehow localized in the region where you measure the probe. But that's not the case. The localization is where the field and where the system and the probe were coupled together. Okay. So a sort of extreme version of that is a sort of cosmological one, that if we now on Earth measure the cosmic microwave background, we're measuring radiation that came from the surface of large scattering. And therefore you could say that we are measuring a local observable, but of the universe at a very early stage of that large scattering surface. Okay, so that's a sort of extreme version of what I'm saying. Okay,
good.
Right. So that's the localization properties. And by the way, all of these are theorems. They come out of the framework once we've made the assumptions that I've stated, including this hard property. The second set of properties refer to the statistics of what we'll see. We chose our induced observable so that we would get exactly the right expectation value. That was how things were defined in the first place. Oops, excuse me. So obviously this map epsilon sigma is an important thing. It maps from the probe algebra to the system algebra. It's a linear map. It's also completely positive. So it maps positive things to positive things, and it goes on doing that if you tensor in a finite dimensional system. And there are some important properties. It maps the unit in B to the unit in A. It preserves adjointness. So if we apply it to the star of B, we get the star of whatever we get if we just put B in. So in particular, if B is self-adjoint, then so is epsilon sigma of B. And on the other hand, it is not a homomorphism. That would be the simplest thing you would find. But what you actually get is this property here, that if you take a general observable B and then form epsilon sigma of B star epsilon sigma of B, this is less than what happens if we get epsilon sigma of B star B. And the less than or equal to here is in the sense of comparing operators. It means that if you take away, if you, subtract this operator from that operator, what you're left with is a positive operator. Okay, and the physical interpretation of that is that the true measurement, the one we actually make on the coupled system, so that's this observation of B tilde in the state omega tilde sigma, this actually ends up having a greater variance than the hypothetical measurement, which is of observable epsilon sigma of B in state omega. So we have a greater variance in the true system than in this hypothetical one. And the interpretation of that is it's because of the detector fluctuations. And so there's the expression there. The variance in the hypothetical measurement is less than the variance in the true measurement. And the same properties of this epsilon sigma map then transfer to the discussion of effects. So an effect is an observable, so that B is itself positive, but also 1 minus B is positive. And we interpret the B as being an effect happening and 1 minus B as being the same thing but not happening. So it's a sort of true-false measurement. And the probability of B occurring in state omega is just the expectation value of B in omega, and the probability of it not happening is just the expectation of 1 minus B, and those will sum to 1. In quantum measurement theory, you not only have effects, but you would have effect-valued measures, and so this would take some open set, which might be a range of possible experimental outcomes, and map it to an effect. Okay, so if X is some range of possible outcomes, E of X is an effect, and the probability of getting that, the expectation value here, is to be interpreted as the probability of getting a result in range X when your state is omega. So we can take any such effect-valued measure on the probe and put it into our framework and translate it into a system effect-valued measure, just by putting it into the epsilon sigma map. And this effect-valued measure will generally be unsharp. So the whatever we start with, B might be projector, but epsilon sigma of E of B will not in general be a projector. So the actual measurements we make on the system are typically unsharp measurements. So now I want to shift a little bit to the discussion of states, and we're going to use these effects. Let's suppose we measure an effect B, and we test it when the system state is omega, and we want to know, we want to know what should the state be after a successful test of B. So I'm going to use the term post-selected for this. I know other people use that term for something slightly different, but the post-selected system state conditioned on this effect B being observed should be useful for something. It should give us a correct prediction of probabilities of any system effect being observed given that B was. So it's a conditional probability definition. And we can compute what this state should be afterwards. And we do it like this. So there's our probe effect B, and consider any system effect A. Well, the probability of those two things both being observed when we start in system state omega and probe preparation state sigma can be given by this formula here. And I'm just going to rearrange the symbols a little bit and write that as this I sub sigma on B of omega applied to A. So this is a slightly complicated way of writing all of those things down, but it's going to be useful to express the change of state as a map on the set of states. So our conditional probability of A given B is, of course, just the probability of seeing them both divided by the probability that B was observed. And that can now be expressed as a ratio of two things here. And so assuming that this denominator is non-zero, then we can compute the normalized post-selected state. And it's just given by the result of mapping our initial state omega through this I sigma B sausage machine, if you like, and dividing by a normalizing factor, just to make sure that when we plug in 1, we get the expectation value 1 coming out. So that's going to be our definition of the post-selected state. And it was, as I say, it came from a definite idea of what this system state should do. Okay, it's all based on this conditional probability definition.
Chris, can I ask, are you requiring that after I perform this measurement that the system is in an eigenstate of this measurement? No. Is that a way of interpreting it? No. Okay. So it can be.
Yeah. What I'm requiring is simply that this is what the state should be afterwards. Okay. It should be a state in which probabilities going forwards of other system effects can be correctly observed, conditioned on the fact that you have seen B happen.
I guess the reason I'm asking is because a lot of these kind of restrictions on measurements in the setting come about because, you know, if you, I think with like, I don't know the Sorkin one, but I'm guessing that one gets superluminal communication because one's requiring that the post-measurement state be in an eigenstate of the measurement result. Yeah. But it sounds like here you're just asking that given the post-measurement state, I could calculate after the result of any I could say if it was in an eigenstate of the measurement, this is what I would, the probability of if I were to perform further measurements on this state, this is what I would get. I could compute it. Okay.
Yeah.
So I guess I'm thinking of the case when I have, you know, a bunch of different regions, and if I am allowed to perform an arbitrary measurement which projects onto eigenstates, and I can clearly superluminally signal. So measurements that do that need to somehow not prepare.
Yeah, exactly. So you're exactly right. That's what you worry about. Okay, and that is more or less what Sorkin's example does.
Right.
And what we want to do is not prejudge too much what this state is. Okay. I want to say, what should it do? Let's see if we can calculate it, and then let's see what follows from that. Okay. So I don't want to say, okay, it's got to be an eigenstate. What I'm going to say is it's got to have this property that I've highlighted here. It's got to be useful for computing these conditional probabilities.
Okay. So for example, if I have a bunch of regions and in each region I get some data which then would allow me to reconstruct what the eigenstate was, does that satisfy your does that satisfy this condition?
I'm not totally sure what you mean by reconstructing the eigenstates, but anyway, let me continue and we'll see, because I will come to the multiple region example in just a second. Yeah. Okay, so this is how we are going to define the system state, and what I just argued is that you can actually write down a formula for it. So we're not saying it's got to be an eigenstate, we are saying that in the end it comes out to be given by this formula here. Okay, and the ingredients in that formula are just the scattering map and the probe preparation state, effectively. Now, there was a question earlier about what is non-selective measurement. Well, let's consider that here. I'm going to essentially destroy the evidence afterwards. So I measure an effect, and I either get the answer yes or I get the answer no. And essentially, this state that I'm going to construct is going to be the convex combination of those two post-selected states, weighted by the right probability, the probability that they occurred. And if you work that out, here we go, then you find that you're just taking the sum of these two states like so. And because this depends linearly on the first argument, they actually sum together and B actually cancels out. So it turns out that non-selective measurement gives you a state that doesn't actually depend on which effect you were trying to measure. And that's because you are essentially suppressing all the information about that measurement. Okay, so there are more locality results that come from this. One is that if we have an observable that's localizable in the causal complement of the coupling region, we can write a formula for the expectation value of A in this updated state omega prime. And it turns out to take this very simple formula here. It's a ratio of two expectation values. And we can use that to figure out the conditions under which the expectation value is unchanged. And it's, of course, completely equivalent to A being uncorrelated with our induced observable in the state omega. That's exactly when we would get a factorization and a cancellation to get the original answer again. We also find, by the way, that the expectation values are always the same in the case of non-selective measurements taking place in this region K, or with coupling region K. And in general, you find that the expectation values in the original and updated state are different. And in fact, there's a case where you can easily analyze what's going on. If you take a state like the Minkowski vacuum state that has this so-called Ray-Schlieder property, you can see that the only occasions where we will get unchanged expectation values are when the observable that we were looking at was just some sort of, the test we were making was a trivial one, a multiple of the unit. Okay, so in general, post-selection alters expectation values everywhere in space-time. I've just given you an example, an illustration for the causal complement. With more work, you can say something about the future and past as well. But we see also what that's about. It's about correlation, and I think there's nothing surprising in that. A further point, however, is that there doesn't seem to be any good reason for putting in a rule to say that the state omega instantaneously changes to omega prime across some surface. Okay, we looked at various properties that this omega prime has. No surface seems to be at all distinguished by those properties. So we haven't found any real reason to put such a rule into the game, and either from necessity or desirability, which actually was a slight surprise to us. So here comes the successive measurement of probes. So we're going to consider two probes, B1 and B2, and they're going to have coupling regions K1 and K2, and therefore scattering morphisms, θ1 and θ2. There's also going to be a combined probe with the coupling region in the union of the two couplings and some sort of combined morphism θ. So the interesting situation is where there's trivial intersection between K2 and the causal past of K1. Okay, and under those circumstances, at least some observers will say that K2 is later than K1 because we can put in a Cauchy surface that separates them in that way. Now, it's very natural to assume that the scattering morphism for the combined system actually factorizes into the two periods of evolution. It should actually factorize as a composition of θ1 and θ2. The scattering morphism was actually defined so it maps from the future to the past, which is why θ2 here turns up before θ1. So this is a very natural assumption, and it is actually something you can prove in some models. And here we, of course, have a threefold tensor product between our system and probe 1 and probe 2. So we have to insert these scattering maps into different places in the tensor product, which is what this notation is about here. So under those circumstances, what you can prove is a coherence result, which says the following. Let's consider a measurement of effect B1, and our probe 1, excuse me, is going to have preparation state sigma 1. And then after that, we consider a measurement of probe B2, and its probe is initialized in state sigma 2. So these are done with different probes. So after the first effect is successfully observed, we have an updated state. We feed that state into our second measurement, then we get a further updated state. And the theorem is that this is the same as if we just treat these two measurements as a single combined measurement of effect B1 tensor B2, okay? And we use initialization state sigma 1 tensor sigma 2. So the same overall state comes out when we think of this as one single measurement, or if we think of it as this one followed by that one, okay? And this is quite important because in the case where the two regions are in fact space-like separated, we can use it to argue that our measurement rule is independent of any causal order between them, because in the case where they are causally disjoint, we can say that some observers think K2 is after K1, but other observers think K1 is after K2. So we use the result we just proved, which is because some observers think K2 is after K1, and that gets us to this formula for the state change map. But then some observers think that K1 is later than K2. So we apply the same argument again, which gets us back to this composition here in the other order. So our rule for updating the state is independent of any causal ordering, which, if you recall, was one of the constraints we wanted to make sure would be satisfied in the theory. Okay, so now I want to come to this impossible measurement thing. I notice we're just over an hour. Is it okay for another 5 minutes? Yeah, okay. So going back to this impossible measurement setup of Sorkin, this is the recent paper preprint with Maximilian Rupp and Henning Bostelmann. Here we go again. We have Alice, Bob, and Charlie, and Bob's laboratory partly overlaps the future of Alice's and the past of Charlie's. So Alice is going to choose whether or not to make a non-selective measurement of some effect, which is going to be measured using a probe and a coupling localized in this region here. Bob, we're going to say, is definitely going to make a non-selective measurement using his probe. And the question is whether or not Charlie can determine whether or not Alice measured or not. So if I use omega B to denote the state updated on a successful measurement of B, but without the measurement of A, and omega AB to be the update conditioned first on a successful measurement of A and then on a successful measurement of B afterwards, the question is whether or not the expected value of C changes between these two states, okay, when C is an observable localized in that region. And what we can do is analyze it in the following way. We model A and B using probes, and then a little bit more investigation of the locality of the scattering map shows us that we can say something about what happens when we take C tensor 1 and hit it with the scattering map for the coupling due to B. And the upshot is that we can say it is localizable in region N. And region N sits in the in region for B's measurement and in the causal complement of A's coupling region. So this is the geometry that we can always arrange. Okay, so that's the geometrical part of the paper, if you like. And this allows us to see that Charlie can't determine whether or not Alice measures, because here's the formula for the expectation in the state consequent on successful measurements of both A and B. Okay, we have these probe preparation states sigma 1, sigma 2. both scattering maps and our operator C. But when we let θ2 act on this observable, then it lives in region N, or it is localizable in N. And we know that θ1 acts trivially on N. So the θ1 actually drops out, and we may as well only have had θ2. And then sigma 1 is actually just a passenger in this whole game. And the result is just the expectation value of C in the state updated conditioned on a successful measurement of B. So there is no way that C can determine whether or not A has measured in this protocol. In other words, there is no Sorkin type pathology in our measurement scheme. The assumption going into this is this locality of the scattering map. And this is really saying that the probes and the couplings must be determined by local physics. Okay, and under those circumstances, there is no superluminal signaling. Again, it's exactly what you would hope, but as Jonathan already said, you worry in measurements of quantum fields that you might have introduced some superluminal signaling through the measurement description. And the slogan that we came up for this paper was that impossible measurements of the sort Sorkin described therefore can only be performed using impossible apparatus. In other words, apparatus in which the probes or couplings involve non-local physics, okay, which we don't see in the real world. So that's the main result. I want to very quickly just tell you that there are specific models that you can compute everything in, and those are where you have two scalar fields coupled together by a quadratic coupling in the Lagrangian, and everything can be computed. Given view of the time, I'm just going to, I think, skip over this and go to the conclusion, which is the following: that we've, I hope, successfully adapted this operational framework of quantum measurement theory to AQFT. It's fully covariant. It's formulated for curved spacetimes as well as flat. It uses fairly minimal assumptions on the theory. We try not to put in ad hoc assumptions. And then everything else is derived from those. The headlines are that we get local system observables coming out of probe observables, and the localization is where the coupling took place. We have a rule for post-selected states. It's derived from required properties rather than being posited. It's coherent under the successive measurement, and therefore invariant under reordering in the causally disjoint case. Coming to state change across surface, when Rainer Fesch and I started, we were rather hoping, or well, I don't know, not hoping, but we were expecting really to see that the viewpoint of Helvig and Krauss might be vindicated in some way. But in the end, we came to the view that there's no need of this hypothesis. We don't see any reason to introduce a rule that says that the state jumps discontinuously across some surface in space-time, because no surface seems to be particularly distinguished. And finally, we can show that our framework has no impossible measurements. And with that, I'll thank you for your attention.
We have a problem with the
Yes.
when everyone's got their microphone off.
Yes.
Good. So does anybody have any questions?
I have a question. Thanks a lot, Chris, for that talk. That was really nice. I sort of have three questions that are kind of sort of related. So the first thing is with your measurement model or measurement scheme, it seems to me like what you're doing is you're how to say, somehow the axiomatic formulation of the quantum field theory requires postulating that the observables are associated with that algebra of local observables.
Yeah.
And I usually think of that algebra somehow as being associated with like projective value measures or self-adjoint operators, like maybe that algebra could be spanned by, say, the polynomial field operators or something like this.
Yes.
Right? So now what I'm wondering is that the fact that now you've given a more general notion of a quantum observable in algebraic quantum field theory in terms of these effect valued measures, does this affect, no pun intended, but does this affect sort of axiomatic formulations of QFT?
We're supposed to give them a better foundation, if you like, because this, you're quite right that normally you might think of a local algebra as being generated from smeared fields where the smearing goes on in that region, okay?
Yeah.
And this is supposed to be somehow about what you can measure in that region.
Right.
But usual treatments don't actually tell you how you would go about measuring it at all.
Yes.
And therefore the claim that it is something measurable in that region is sort of unaddressed. And maybe I will just go back and show you what does happen in this case where you have the smeared fields. Okay, this is probably the easiest. So here is a smeared field of the probe.
Mm-hmm.
And under this map, epsilon sigma, it gets mapped to a smeared field of the system. Okay, the smearing is different. And to figure out what this F minus is, you need to look at the dynamics. Okay, it's sort of scattering behavior, but there's a formula that tells you how to work out F minus given H. And indeed, F minus is localized in the coupling region. H can be localized anywhere you like. Okay.
Right.
So in a sense, what this says is that phi F minus is measurable using a probe, okay, with a coupling that is localized in this region K, okay, which is only just a bit bigger than the support of F minus.
Okay. Yeah, so I guess I'm just kind of wondering is like, do we need a new axiomatic formulation in terms of like effect or POVMs or effect value measures associated with a local region as opposed to the usual formulation? Or maybe...
Yeah, I hope it's basically the same formulation.
I see. Okay.
But with providing it with the measurement rules, essentially.
I see. Okay, and then I think I had two follow-up questions to this. Is that the scattering morphism? I usually think of I'm supposed to think of this in the standard measurement theory as like the interaction Hamiltonian that couples the probe and system in some sense.
It would be more like the interacting time evolution, something like that.
Okay.
But it's mapping from the far future to the far past. Yes.
Right. So then, are there? And I know that the restrictions you imposed in your talk were like locality of this in some sense. Are there further restrictions that should be imposed on this in terms of like energy constraints or something like that that would further restrict?
Oh yeah, yeah. You could well imagine that. We really just wrote down an axiomatic idea of what a coupled theory should be. Okay, and that was, where did I write it? Just here. So the statement that there are some isomorphisms outside the coupling region. Okay. Right. And yes, for sure, you could imagine demanding that this coupled theory is well behaved in many ways. Okay. And that will affect what you can measure.
Right.
It's a live and it's an open question, actually. How many of the observables in this local algebra can you measure using a measurement scheme? That's what my student Maximilian is working on at the minute to try to figure that out.
That was exactly my next question, because you might imagine that all elements of the algebra aren't equally measurable, and maybe like, you know, phi to the 10 is harder to measure than phi to the 1 or something like this, and there's an energy constraint or something that's scaled.
Yeah, but I think that's a very good question, whether you can grade the individual elements by how hard to measure they are. We hadn't thought of doing that, actually, but at the moment we're just looking at the question of which ones can or cannot be measured. We suspect that the answer to which ones can be measured is basically some dense, at least some dense subalgebra, something like that. We don't know for sure if it's the whole thing. But of course, you know, dense might be good enough, because to all intents and purposes, you'd never be able to tell the difference in practical terms. But yeah, it would be nice to actually say on the nail, it's all of them.
Well, thank you.
I mean, that was a question I had as well, in the sense of there's a result due to Lev Weidman where he asked the question, you know, given some, it's not, you know, given some surface, some space-like hypersurface, can all measurements be performed instantaneously? And his answer is yes, but you need to do teleportation. You know, he basically uses a teleportation scheme, so that in some sense everybody's teleporting their systems to one region, the measurements being performed there, and then only at some later time far in the future do you compare all the different measurements and show that and reconstruct what the result is. So the result there seems to be that all measurements can be performed, and I guess I was wondering, it wasn't clear to me whether your post-measurement, so there it's very important that the post-measurement state is quite random, and so I guess I was wondering if you found that you couldn't perform all measurements, would that cause you perhaps to revisit your restriction on what kind of post-measurement states are allowed?
I don't know about
because it wasn't clear to me how wedded you are, how rigid that the requirement is that you have there.
So you could certainly weaken it a bit. Okay, we took the view, and this actually is also what's done in quantum measurement, that you have this updated state using an instrument, and that is essentially how they do it in quantum mechanics. So we took that over to the quantum field theory viewpoint. You could weaken it by saying, well, it's got to be approximately that. Okay, it's got to be something close to what will give you the right answers going forward. Of course, it's then very difficult to analyze something like that, where you say, oh, well, it's nearly the right answer, because then you have to say, well, how near? But you certainly could weaken that assumption slightly and see what you could do, but I don't know. Yeah, I mean, then you'd have sort of thrown away the guiding principle, and that would be quite difficult perhaps to deal with. I guess the question of whether all of the local observables can be obtained using probes, provided you get density, then you might say that's enough, okay? Because we know that the experiments we do are only performed to finite accuracy, and we're only going to make finitely many of them. So you will never know for sure that you've got two identical observables, right? So this, if you want to compare two observables, you'll never know whether or not they are exactly the same. But if you can get as close as you want, then that might be good enough.
Well, I guess, I mean, so Weidman's conclusion, I don't think is that it's not just about local measurements, it's that all measurements can be performed.
I should look at this. Roughly when was that paper, by the way?
Ooh, I can forward you the.
Yeah.
I can forward you the. I can dig it up. It's quite a while ago. I guess there's been this thing resulted. I guess people have been interested in things like how does quantum information flow in space-time? If you have many separated observers, can they do a measurement? Can they implement a CP map if they're very far apart? So it's that whole literature.
Yeah.
I'm happy to send you that. But I guess there it's crucial that you seem to be requiring that the post-measurement state allow me to get measurement outcomes going forward. And I guess it's not clear to me why I should demand that. You know, I just, at some moment in time, people all across my region of space-time perform this measurement, and that's it, that's the measurement, and we don't care what happens afterwards. Or I guess the question is why should we care what happens afterwards? You performed our measurement.
Well, I guess the question is, can you, so you make some measurement now, And then going forwards, other things happen. You might want to regard some of those things as part of a bigger experiment.
But usually measurements disturb the system, and most measurements are very destructive in a particle accelerator, or usually I measure it and I've disturbed my system and that's the end of it. I guess it's unclear to me why here I would expect me to continue in any way. I mean, it may be an I'm obviously it's an interesting requirement, but I guess I'm just wondering why one is wedded to it, in the sense that I guess the question is, given some conditions on measurements, what kind of measurements can you perform? And it may be that to perform all measurements, even the non-local ones, one needs to get, why hold on to that postulate, I guess, or that requirement?
Well, I suppose you could say, yes, there are destructive measurements, but then maybe you should start by saying, well, at least we understand the more ideal case where there is the possibility of further measurement, and that ought to be a coherent thing. So that's what we've done. Okay, so in a sense, it's like the basic quantum mechanics idea, where you say, well, immediately afterwards, then you should be able to repeat the experiment and all the rest of that. We're trying to take those ideas over to quantum field theory. Of course, you're right. If the measurement is very destructive, then it might not be so interesting to apply this rule. Okay, but that's because the actual experiment is less than ideal in some way. Okay? We'd like to say that you could have an idea of a careful or non-destructive measurement that would obey these rules, and where you could measure and then, having updated your knowledge, make successful predictions for what will happen in the future. So after all, I mean, we're talking about the field theory. The field theory isn't destroyed. An individual electron or something might have been destroyed, but you can for sure still continue to measure the electromagnetic field after what's happened in the particle accelerator.
But you have disturbed the field greatly, usually, by your measurement.
Yes.
So
yeah, that's right. Yes. Yeah. But this will actually take into account the dynamics of that interaction, because we are in principle modeling the coupling between the two fields involved.
Great. Are there any further questions for Chris?
Maybe I have a silly question, or maybe it's not silly, but I was wondering if you can use this. So usually, I guess, with measurements or like open systems, you can write everything as just an effective theory on the system you're interested in, using completely positive maps, etc., etc. Do you think that you could do this here to study, I don't know, like quantum field theories with fundamental information loss or something like that, and try and axiomatize how they might work?
Yes, actually. We did think about this, Rainer and I, briefly, that you could almost regard this as a way of modeling quantum fields on non-commutative backgrounds, that the measurement almost resembles what happens on non-commutative backgrounds to some extent. Likewise, you could say that your quantum fields with loss is because it's actually a quantum field theory, but where there are some of the fields are not visible directly to you. The ones that you have no direct access to. They interact with things that you can access, but you never directly access them. And then indeed, you could probably use this framework as a sort of basis for that.
Okay, so would that be like, I guess, would you change something like the time slice axiom to some completely positive map from one Cauchy slice to one in the future, or something like that?
That I hadn't thought about. I mean, to some extent, this epsilon sigma map, if I just point at it again, is this CP map. So
yeah.
What is mapping us from, because it's got this conditional expectation. That's where it's CP, and that breaks the homomorphism property, but just leaves you with CP. To some extent, this is, if you like, a blurred out version of what B was in the first place.
Yeah.
Now, how the time slice goes with that, I'd have to think. It's not obvious to me quite what's going on. But what I would hope is that you can avoid making up too many rules. So you set the theory in the first place, and then try to derive as much as possible from the assumptions you made. So you could say, right, suppose we have a quantum field theory. There are 3 or 4 fields. One of them you have no access to directly, although it couples to things that you can.
Mm-hmm.
And then you could see what's the phenomenology in such a theory. And then look for an effective description in which there are only 3 fields, right? The ones you can actually see.
Yeah. Yeah, that sounds interesting. Thank you.
Great. Are there any other questions? Good. So, Chris, thanks very much for your time. I really appreciate it. I've come up with a solution for the problem that people can't give applause when their mics are muted. So I'll end this with giving you some canned applause that we found.
Thanks, Chris.
Pleasure. Yeah. Very nice.
Yeah, I think, yeah, there's also the emoji.